So, good evening, everybody. Today, we are going to teach about Stefan's constant MC method, practical in virtual lab. And there is one more recording in from NIT Bangalore. So, I am going to show you those two practical sessions, how to find the Stefan's constant using Stefan's constant apparatus by virtual lab.
Welcome, dear students. Today we are going to perform the practical with the aim to determine the Stephen Boltzmann's constant. So to perform this practical, we need to go on vlab.amrita.edu. So first of all, you need to go on this URL. The home page of this virtual lab is loaded. Now you have to over here on physical sciences. Then you have to go in this tab that is heat and thermodynamics virtual lab. Then you have to go black body radiation determinations of Stephen Boltzmann's constant. So now we discuss the aim of this practical. So aim of this is to determine the Stephen Boltzmann's constant, and it is very clear. Apparatus is conducting the heater, the temperature indicator, box containing the metallic hemisphere with a provision of water flow over it and suitable black body which can be connected at the bottom of this metallic hemisphere. As we know that the emissive power of any surface is given using this formula. E means the emissivity into sigma into T to the power 4. And we know that the value of Stephen Boltzmann's constant is 5.67 into 10 to the power minus 8 watt per meter square into Kelvin to the power 4. This is the two scientists who derive the formula to calculate the emissive power of black body, that is Joseph Stephens and Boltzmann. And that's why it is called as a Stephen Boltzmann's law. Now, let us understand the apparatus. So first we fill the water in the heater chambers. Then we start the heater. So the water is heated in this heater. Then we flow the hot water on the surfaces of hemisphere so that the temperature of hemisphere is becomes same as the temperature of water. And then here we have arrangement to provide the black body at the bottom of this hemisphere. So now let's we discuss how we are going to calculate and mathematical steps for that. So we put a copper plate over here. First, we have calculated the mass of this copper disk as well as the specific heat, that is Cp, is also there. And we need to calculate this rate of change of the temperature, means dt by dt, that is variations of temperature with respect to time. And here we know that the heat is transferred from hemispherical side to this black body by means of radiation, and that is given over here, that is sigma into A into T. So this is the heat which supplies or which is increases, and we calculated the temperature increases using the formula that mCp delta T. And now we know that the heat transfer by the radiation from hemisphere to black body equals to the energy stored in the black body. And that's why we compare this equation number 3 and 4. And based on the comparisons of equation 3 and 4, we make a subject sigma. And using this m into Cp,
divided by a into th to the power 4 minus dt to the power 4 into dt by dt. That formula is useful to calculate the Stefan Boltzmann constant. So now we are going for the procedure. The procedure is very similar that we discussed. First, we need to remove the disk from the bottom. Means we need to remove the black body from the bottom of the hemisphere and then switch on the heater and allow water to flow over it. Allow the hemisphere to reach the conditions, note down the temperature T1, T2, T3. That temperature sensor is feed the hemisphere. So this procedure is to make the temperature of the hemispherical cell in steady state conditions. After reaching the steady state conditions of hemisphere, we need to keep the disk of black body at the bottom of the hemisphere, and we need to note it down the rising temperature with respect to time till the steady state is reached. Means we have to plot the variations of the temperature of black body with respect to time, and we note down some of the points. And after marking that point, we need to plot one line which is passing through that points, and then we need to calculate the slope of this line, and the slope of this line is dt by dt, that is the temperature gradients with respect to time. So using this graph, we can able to get dt by dt. After calculations of dt by dt and various properties of black body, that is mass and Cp, as well as the area, we can able to find it out the Stefan Boltzmann's constant. So now a procedure to perform the simulators, it is very similar to the experiment. We need to set the water temperature. It is lies in the range of 0 to 100. Surrounding temperature is also there, minus 10 to 99 degrees centigrades. Mass disk is there from the 6 to the 10 grams. Radius of disk is also having a variable from 0 to 5. Then there is a reset button. Then feed the disk. Means in beginning we need to remove the disk, and after that when the hemispheres is reached the steady state condition, we need to feed the disk. And here for the measurement of temperature, the T1, T2 and T3, we have the various channel is given. Also we have a stopwatch to note down the time to reach the probe in the steady conditions. So this is the observation table. We have to run this experiment for the trials. Then we have to note down the temperature T1, T2, T3, T4 and the time to reach the steady state conditions. Mass of the disk is there in kg, then specific heat of the copper, radius of the disk, area disk, then slope we need to know, and by substituting all these variables, we are able to calculate the sigma, and we are able to find it out the value of sigma. So now we go for the next step, that is the self-evaluations. So students, whenever you're going to perform the practical before the simulator, you need to check your knowledge using this self-evaluation sections. So now we directly move towards the simulators. So I just do the login using my Google account. You can also do the same things when you are going to perform. Now see here, there is one kind of error is that there is a click here to enable the flash player. So students need to go over here in the Chrome, click on that red button, then give the permissions to the flash player over here, and then here you can read this message that you need to reload this web page. So reload this, and now the flash player is there. So you have to go on the full screen mode from here. So currently I'm going in a full screen mode. So variation of temperature is there from 0 to 100. So I am going to set down my temperature of water near to 70 degrees. Then the surrounding temperature currently as per the atmospheric temperature I am taking as a 30 degree. Then the mass of disk is there in the 5 grams to 10 grams. So I am taking the 6.5 grams. The radius of disk is there from 1 to 5 centimeters. So I'm setting down 3 centimeters. Using this click button, you can be able to observe the cross-sectional view of our apparatus. Now I'm doing the power. So our water is heated and which is reached to be 70 degrees centigrade. Now you can see here the temperature of T1 is the sensor which is feed over here. T2 is that T3. So we need to measure the value when the temperature drops. So T1 is 70, T2 is also 70, T3 is also 70. So now our hemispherical cell is reached in the steady state conditions with the water, and all the temperatures of these three will show the same value, and that is a 70. So now I'm going to pick the disk and I have to measure the temperature 4. So I'm going to measure currently the black disk is in thermal equilibrium with the surrounding. That's why it shows the 30 degrees centigrade because the surrounding temperature is that. So now we need to start the stopwatch as well as the feed the disk. So here the program is set. When you click on the feed the disk, the timer will automatically will start. So you need to note it down the results after